So, regularity theorem, we say if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So an altitude, think of it as like the height of a triangle. So looking at triangle ABC, the altitude is CD. That's your altitude. So we drew an altitude from angle C to our hypotenuse. So if I flip the orientation of this, it would look like this would be C, this would be B, and this would be A. My right angle's there. Just flipping the orientation. So we can compare. If we do that, you can see now it makes up two similar triangles. When we draw this altitude, now we have triangle CDB or CBD in red, which is similar to our blue triangle CDA. And by similar, remember we mean that our sides are proportional and that all of our angle measurements are the same. And these two triangles are congruent to, we kind of trace them out in green, this larger triangle that makes up the two of them. So it's kind of like, have you ever seen one of those word image riddles? I don't know what you would call it, where it's like, how many triangles are actually in this picture? Well, in this picture, we have 3 of them actually, and all 3 are similar. So in this just first example, we're going to identify the similar triangles in the diagram. So let's just draw the ones that are made by using our altitude, which would be TU. Our first triangle, let's do this, how we do the blue one here. I'm going to try to draw them so all the orientation is the same of all the triangles. So knowing this would be angle U, this is angle T, and this is angle R. Our other similar triangle be like this. Where to draw it out, we would have this is angle U. And then this would be angle T up here. And this would be angle S. And then we pull out our largest one, which like we kind of had by doing kind of our border around the two. So this is T, S, R, where T is our right angle. So we could write a similarity statement that says all these 3 are the same. We could say triangle TUR is similar to triangle TUS, which is similar to triangle STR. And I made sure that I was going in the same orientation for each of these. I went clockwise, TU to R, TU to S, ST to R, so I know my vertices are matching up with what they should match up with. Not a super interesting example, but I think for at least me, maybe I'm just not good at it. It does take some like mental energy to kind of pick out where they are and write them in the same orientation. Kind of have to like do a little bit of mental gymnastics. But let's throw some numbers into the mix now. We have a roof that has a cross section that is a right triangle. The diagram shows you approximate dimensions of this cross section. Find the height h of the roof. So I'm going to, like I did in the last problem, I'm going to pick out all my, thank you, similar triangles. So my largest one, we want to call it, we've been calling it kind of our largest one, our green one. We could say we're trying to flip the orientation to be the same. We could say this is y, this is z, and this is x. It's our right angle here. Where the length from y to x is 3.1. The length of z to y is 5.5. The length of z to x is 6.3. So I'm just taking those right off of the diagram. We kind of flipped, kind of rotated this by, I don't know, 90 degrees, so it's sitting flat. All right, so that's one of our triangles. Another similar triangle that we can use is if we're trying to find what h is. So for h, I'm going to try to use this, my smallest similar triangle here. So if I flip the orientation again, just so it's matching up, this right angle is w. This angle here is x, because I just kind of did a mirror reflection of this one. So this is x here, and y would be up top. So you can see now on this triangle, y to w is h. And we're also given y to x, which is 3.1. And we don't even need to draw the third triangle because we can already set up a proportionality statement. We could say we know these two triangles are similar. So we could say xz, so our hypotenuse of our green triangle, is proportional to the hypotenuse of our red triangle. Then we could say that zy, so I don't know if we want to call this the height of our green triangle, is proportional to the height of our red triangle. So YW. And then we can plug in what we know. We have 6.3 divided by XY in our red triangle. I should do this because there's an XY in here, but also in here. So making sure that you're using the right one. XY is 3.1. I guess it doesn't really matter because they're the same actual length. 3.1. So you go to, so ZY, this is talking about our green triangle. This would be 5.5. And this is over YW. That's H, what we're trying to find. So we can't get away with it. It's back, more cross multiplying. We have 6.3 H is equal to 5.5 times 3.1, should be 17.05. We divide each side by 6.3. So 6.3, we get out, it's about, we're on just a 1 decimal spot, 2.7 meters. That's what our answer is. So like I said, this part down here I think is easy because it's what we're used to. We've been doing this for a while. Once we have the setup, it's easy to go from there. I think the challenging part is setting up with kind of what side length am I actually talking about and how can I set up that can find what I need. My biggest hint when you're doing that, draw a picture. All right. So next thing we have kind of just a short piece on the back. Just 2 example problems. This is more kind of a preview, kind of a process we're going to need to know how to do come Tuesday for the notes. So I thought I'd introduce it now so you can get some extra practice. So come Tuesday, it'll be super easy. And it's not challenging at all. We're going to find what's called the geometric mean, which we'll use on Tuesday, and we'll get out how we use it on Tuesday. But the geometric mean is a positive number that satisfies this proportionality here, saying that a over x is equal to x over b, where a and b and x are all numbers. So if we're cross-multiplying those 2 values, we would get x squared is equal to a times b. So your geometric mean, x, you find by taking the square root of a times b. So if we have 24 and 28 in this first example, this is a and this is b. So to find the geometric mean, we could say, well, it's x squared equal to a times b. Or it was x is equal to the square root of a times b. So if we just take 24 times 28, you get out 672. So you have x is equal to the square root of 672. And again, that's what we would call one of our exact answers. You always got to check if you can fit a perfect square into that. And I know I don't want to try to go and guess and check what perfect square it is, but I have it written down. The largest perfect square that goes into 672 is 14. So square root of 672 we could take by taking the square root of 16 times the square root of 42. And then this number simplifies because it's a perfect square. So this would be 4 square root of 42. That is our geometric mean. 4 square root 42. So pretty simple process. Take the square root of a times b and simplify it if you can. So for b, we could just take x is equal to 8 times 10 is 80, which we can simplify this as well. 80 can be split up into the square root of 16 and the square root of 5, because 16 times 5 is 80. So then we have 4 square root of 5 as our final answer, or our geometric mean. One little hack to make these easier. Sometimes I see people put their perfect square on like this tree branch. If you put your perfect square first and you keep simplifying down, it'll stay to the front, because when you write this, you don't want it in the back, you want it in the front. So I would just always put my perfect square first.